In this class, I would like to explain Raman effect. When a monochromatic light is allowed to pass through substances like solid or liquid transparent substances, there is a decrease in the intensity of the scattered light. This is observed by Rayleigh, so this is called as Rayleigh scattering. When a monochromatic light is allowed to pass through transparent substances, either solid substances or liquids, the scattered light intensity decreases. This is observed by Rayleigh, so this is called as Rayleigh scattering. But during 1928, C.V. Raman observed that in the scattered light there are frequencies greater than that of incident light and also frequencies less than that of incident light. So, Raman found that the scattered light consists frequencies greater than the incident light frequency and less than the incident frequencies. These lines are called Raman lines. The spectral lines whose frequencies are greater than the incident light frequency are called as anti-Stokes lines, and the spectral lines which are having less frequency are called as Stokes lines. And these three lines are called as Raman spectrum. Raman spectrum. This is the incident light. Anti-Stokes line. Anti-Stokes line. Stokes lines. Stokes lines. So, the frequency of these anti-Stokes lines is greater than the frequency of the incident light, and the frequency of the Stokes lines is less than the intensity of less than the frequency of the incident light. This is what is called as Raman spectrum. So, the change in frequency delta nu depends upon the frequency of the incident light, and the displacement of these Stokes lines and anti-Stokes lines from the original line depends upon the scatterer substance, nature of the scatterer substance. These lines are highly polarized line. The Stokes and anti-Stokes lines are highly polarized lines. And also the anti-Stokes lines are weaker than the Stokes lines. The anti-Stokes lines are weaker than the Stokes lines. Due to this Raman effect, the rotation and the vibration state of the molecules is affected. During this Raman scattering, the rotation and vibration state of the molecule is changed. This is purely a molecular phenomenon. This is purely a molecular phenomenon. The delta nu lies in between infrared and far infrared regions. Infrared and far infrared regions. So, when light passes through the transparent material or alkali or benzene and toluene like solutions, the scattered light consists of the frequencies greater than the frequency of the incident light and less than the frequency of the incident light. This effect is called Raman effect. So, the Raman effect is the characteristic property of this scattered Raman effect. The Raman lines are symmetrically situated on either sides of the original line. The Raman lines are symmetrically situated on either sides of the original. That means the separation between the original line and the anti-Stokes line, as well as the original line and the Stokes line, is the same. The reason for this is explained on the basis of quantum theory. On the basis of quantum theory, the experimental arrangement to observe this Raman effect is as shown in the diagram. The experimental arrangement to observe this Raman effect is as shown in the diagram. S is a monochromatic source of light. Monochromatic source of light. Monochromatic means light having single frequency or single color. F is a filter. F is a filter. So, monochromatic light is allowed to pass through the filter, and light with single frequency is allowed to pass through the Raman tube normally. Normally means perpendicular direction. The monochromatic light from the source is allowed to pass through the solution, Raman tube, in which the scatterer solution is placed. The Raman tube is always cooled with a cooling water circulation as shown in the diagram. So, when the light is passing through this Raman tube in normal direction, the scattered light is observed in the left side. The right side part is blackened. That arrangement is called as Raman tube. Here the water is used to prevent the solution from heating effect due to the light. Water is circulated around the Raman tube to prevent the solution from heating due to the incident light. The scattered light is observed from the right hand side through a spectrograph or spectrometer, and the scattered light frequencies are calculated and found that in addition to the original light, in addition to the incident light frequency, there are several other frequencies. Few frequencies are greater than the frequency of the incident light, and few frequencies are less than the frequency of the incident light. Also, the difference between the frequencies delta and nu is also measured. Also, the displacement of these Raman lines from the original line is also measured. And these experimental results are according to or coincides with the quantum theory of Raman effect. According to this theory, this is a collision between molecule and the photon. This is a collision between the molecule and the photon. During this collision, the molecule will change its state into an excited state. So, the energy levels of the molecules are changed. So, the change in the energy level of the molecule, say it is E1 minus E2. E1 minus E2. The energy of the incident photon is equal to h nu. During the collision, the energy of the molecule may absorb energy from the photon. Sometimes during the collision, the excited electron in the molecule will come to its ground state. In this state, it transports its energy, it gives its energy to the incident photon. If the molecule absorbs energy from the incident photon, then the frequency decreases. The frequency of the photon decreases, which gives a Stokes line. Or otherwise, if the photon absorbs energy from the excited atom or molecule, the energy of the photon increases. This gives an anti-Stokes line. The probability of getting this change, the change which gives anti-Stokes line, is less than that of Stokes line. That's why anti-Stokes lines are weaker than Stokes lines. Also, nu As is equal to nu plus or minus nu m. Nu As is equal to nu plus or minus nu m. Here, nu m is the characteristic frequency of the molecule. Nu is the original frequency. If it is plus, we will get anti-Stokes line. If it is minus, we will get Stokes line. That means the difference between these frequencies, either anti-Stokes line or Stokes line, anti-Stokes line with incident light or Stokes line with incident light is the same and is of order nu m. So, the Raman lines are symmetrically situated on either sides of the original line. This Raman effect is used to study the molecular structure of the crystals and also used to study the bond nature of the crystals and to study the spin statistics of the nuclei and also to study the binding forces between the atoms or group of atoms, to study the vibrational rotational energy levels of homonuclear molecules, for example nitrogen and oxygen. For all these purposes, Raman effect is very useful. So, this is about Raman effect. Raman effect means when a monochromatic light is allowed to pass through the transparent materials. The scattered light consists of light with frequencies greater than the frequency of the incident light and less than the frequency of the incident light. In the scattered light, it is found that the frequency of the scattered light is greater than the frequency of the incident light. For few lines, it is less than the frequency of the incident light. This is observed by Raman, so this is called as Raman effect. So, since this is a collision between molecule, scatter molecule and the incident photon, if the molecule absorbs some energy from the incident photon, the energy of the scattered light decreases. That means the energy of the frequency of the scattered light decreases, which gives an Stokes line. Or otherwise, if the incident photon absorbs some energy from the excited atom during the transition of the electron from higher energy level to lower energy level. When the electron takes transition from higher energy level to lower energy level, it releases some energy. If that energy is absorbed by the incident photon, we will get anti-Stokes lines. So, the major difference between Rayleigh scattering and Raman scattering is, in the Raman scattering, we will observe a change in frequency, whereas in Rayleigh scattering, we will observe only a change in intensity.